He comes up from Hamilton. So just with his master's degree, he's always had a special interest in cosmology. So I won't steal your thunder. What you're going to be talking about tonight, no doubt it's got a cosmology theme. So from Auckland, we give you a very warm welcome for Jonathan Park.
Thank you. Good evening. Well, tonight's talk, of course, is what is the universe made of? Now, you could say right down at the bottom level it's quantum fields, but we're not going to go that deep. We'll go up a little bit to the components of the universe being radiation, ordinary matter, and dark energy. And I'm going to have a look at how much of each of those components is allocated to the total energy of the universe. And when it comes to dark matter and dark energy, we'll have a look at why astronomers think those two things exist. Dark matter, of course, is a partly hypothetical particle at the moment, but it seems to fit all the observations quite nicely as a particle. So I've divided the talk up into 6 fairly small sections, except for the dark sections here, they're slightly longer. So we'll start off with a couple of concepts which I think will be useful to know through this evening and also generally anyway. And then we'll have a look at an overview of those components and something called the lambda CDM model, which is the standard cosmological model of the universe. Then we'll have a look in detail at these components for the next 3 sections, and I'll finish off with a couple of interesting final thoughts at the end of the talk. So the concepts, the first is Einstein's famous equation, well, it's actually one of his famous equations, E equals mc squared. And in this equation, E stands for energy, maybe a certain amount of joules of energy, M stands for mass, a certain number of kilograms, for example, and C is the speed of light. And so what it really means is that if we have energy and mass, there's kind of an equivalence between the two, and you can convert one to the other, theoretically, at least, by the factor of the speed of light squared. And so the reason I'm showing this part is because later on we're going to be talking about matter and energy. And as far as the universe is concerned on a large scale, matter and energy, or mass and energy, are virtually the same thing, and they have the same effects. So instead of swapping units from kilograms to energy all the time, we'll just remember that they're the same thing as far as the universe is concerned. Now the next concept is the idea of flat universes versus curved universes. Now, the best way to think about this initially is to get rid of one of the dimensions so that we can just think in two dimensions for a moment. So this is an example of a 2-dimensional universe on a surface. So 2-dimensional, we have no third dimension here. The third dimension doesn't exist, so there's no thickness. These little white dots are our little 2-dimensional galaxies. Now, if you lived in this universe, this one might go forever in every direction, or it might curl around and be a finite-sized universe. So what we mean by a flat universe is really the geometry of it. So in a flat universe, if you drew a gigantic triangle in space, you'd find that the angles would add up to 180 degrees. And this is Euclidean geometry, which you might remember from high school. And 2 parallel lines, or let's say 2 spaceships that head off parallel in straight lines will carry on parallel with each other forever in a flat geometry universe. And weirdly enough, you might think that's a curved universe, but if you just fold a flat surface, a 2-dimensional flat surface, it's still 2-dimensional and it's still flat geometry, so parallel lines still remain parallel and triangles still add up to 180 degrees, the angles, and you could even wrap it right round to a cylinder. So that's still not curved, that's still a flat 2-dimensional universe because the geometry is still Euclidean. So there's our flat universe. So what about a curved universe? Well, if you think of a spherical shape, again, there's no inside of that sphere and no outside. We're just looking at 2 dimensions only, so we're just looking at the surface. And if you imagine trying to draw a circle on a ball, a triangle on a ball, you'll find that the angles of the triangle will add up to more than 180 degrees. So you'll find you can't draw a triangle on a ball with 3 sides and end up with 180 degrees. You'll also find that if you had a couple of spaceships in your 2-dimensional universe and they headed off parallel to start with and both went in straight lines, they'd cross over. So that's the idea of what positive curvature is. And there's another thing, negative curvature, which is the opposite kind of effect. But of course, we live in a 3-dimensional universe. It's a bit harder to imagine what's happening in 3 dimensions, but the idea is that our universe is 3-dimensional and it's something called isotropic and homogeneous. That's called the cosmological principle, which means that in every direction you look or every direction you go, you should find about the same amount of stuff and the same density of stuff. That's on large scale, so you might have to take a cube of a couple of 100 million light years on each side, go and measure any part of the universe and you'll find the same density of stuff everywhere. And our universe appears to be flat from observations. So again, that means a flat geometry or Euclidean geometry. And it simply means, again, maybe parallel lines will remain parallel. So a couple of spaceships heading off in any direction at all will continue, if they start off parallel, will continue moving in parallel lines to each other. And just for completeness, here's the idea of maybe the same universe, or a different universe, I should say, an alternative universe that's positively curved and maybe one that's negatively curved. You'd start off heading off with your spaceships parallel. They'd just go in straight lines as far as they were concerned in this positive one and would cross over. So you can see a flat universe is not flat like a galaxy, so it's not a flat shape, it's the geometry that's flat, and we need special observations to see the flatness, which we'll show you later on how that's actually done, so how we actually found out that our universe is a flat, well, as far as we can see, has a flat geometry. So we'll move on now to the components of the universe. 95% of the energy of the universe is in this dark matter and dark energy, so we don't really understand 95% of the energy of the universe that well. The first 5% here, ordinary matter, is the atoms that we're made out of and that stars and galaxies are made out of. And this is from a simulation over here. Each white dot on the screen there, the tiny white dots, is a galaxy. And so those larger blobs in the simulation are groups or clusters of galaxies. And there's also a lot of gas in here that we can't see. In fact, there's an amazing amount of gas in the universe, which we'll have a look at soon as well. 26% of the energy of the universe seems to be tied up in the stuff we call dark matter, which is identified from its gravitational effects only at this stage. And so this is that same simulation with the dark matter, which is invisible, of course, coloured blue, so you can see where it would be. And that forms what we call a cosmic web throughout the universe. And the galaxies are generally embedded in that dark matter. So there's our cosmic web, all that blue stuff there. Well, dark energy, this is probably everywhere, and I say probably because there are ideas that maybe it's not, but generally it seems to fit that the stuff we call dark energy, which makes up 69% of the energy of the universe, is probably everywhere, and it's the stuff that's causing the universe to speed up in its expansion. So the universe would be expanding without dark energy, but slowing down. But dark energy seems to explain why observations show the universe is now speeding up in its expansion. And we'll get to that a bit later and explain a bit more what that means. And coming in at last place is radiation. Radiation is less than 0.01% of the energy of the universe at the moment. It was much greater in the past, it dominated, but at this point in time, radiation is a very small percentage of the universe's energy. This over here is part of the radiation. It's the cosmic microwave background which fills the universe. And radiation, of course, also includes starlight. So I've mentioned dark energy and dark matter. And this brings us to the cosmological model, the standard cosmological model. This symbol here is lambda. And lambda is one of the candidates for dark energy which fits the observations the best, and that's dark energy as a cosmological constant. And that means this kind of energy that's spread through the universe with a constant density, very smoothly spread right throughout the universe, that grows with the universe, and if we went back in time, we get less dark energy in the past. Cold dark matter is the type of dark matter that seems to fit best for all the observations. That's dark matter as a particle that's moving much slower than the speed of light. Now, if it seemed that dark matter was moving near the speed of light, it would be closer to being radiation, and we'd call it hot dark matter. And there's another one in between called warm dark matter. So there's a whole lot of ways to describe what dark matter might be. It seems to be a particle, no one's seen it yet, no one's been able to discover it or even create it in the Large Hadron Collider, for example. So this is the cosmological model, which also, of course, includes radiation and ordinary matter. It's probably a good time now just to mention that dark matter and dark energy, although they're both called dark something, aren't related necessarily. There's a small chance they might be, but generally they're not considered as related. Dark just means unseen, so dark matter, for example, doesn't reflect light, it doesn't emit light, and it doesn't absorb light. So it's really invisible rather than dark. This model is accepted by most cosmologists, although there are a few who are looking at some alternatives. For example, to dark matter, this thing MOND is called modified Newtonian dynamics. And what they're really saying is that maybe we don't need to postulate that dark matter exists, maybe we need to change the equations, maybe the equations we use are slightly wrong, and maybe Einstein got things wrong. But there's a little bit of evidence out there to show that dark matter really does seem to be more of a particle, and that these ideas to modify gravity don't seem to fit every single possibility, and dark matter seems to be the more simple hypothesis. So these figures that I showed you before are kind of rounded averages from different fields, and they're strongly supported by observations and simulations, known physics and equations, which all seem to match quite nicely. So what we see and what we calculate seems to work out to give roughly these figures. So what happens if we take these figures and plug them into an equation or a computer program? Well, if we take the ones I've showed you there and we take the Hubble constant, now that, if you're not sure what that means, the Hubble constant talks about the expansion rate of the universe as it is at the moment. I've used something called, I've used 67.7 as the figure. There is something called the Hubble tension, where the Hubble constant has been measured by various different methods, and one of the methods is showing the Hubble constant to be about 73. That means a faster expansion rate now than 67. But I'm going to use that 67.7 or so through the talk tonight, just for the figures I've shown. And I'll show you at the end what the difference would be if we looked at 73 compared to 67. Okay, so take these figures, put them into a computer program like I've done here, and we get a plot of the expansion history of the universe. So what does this mean? Well, the bottom axis here is the distance in billions of light years, and the vertical axis is time in billions of years. So I've done this to scale in that each little tiny box there is 1 billion light years by 1 billion years. You've probably seen this picture, I think there's one up on the wall there as well, which is the same kind of thing, but not to scale, although it might be some sort of logarithmic scale maybe. But this is good because it does give you an idea of expansion in the very early time of the universe and the accelerating expansion. But if we just sort of bring that down to size to this graph here and then kind of pinch the bottom and then stretch out the top, it shows you the more realistic scale. Now the bottom line here is actually 380,000 years after the Big Bang, because that is the time when light was able to travel freely through the universe. So the oldest light we see, which is the cosmic microwave background, comes from this time of the universe. So I'm not worrying about the first few thousand years before this. So why have I chosen these figures? I've chosen 2 points at the bottom here, 84 million light years apart at that early time. So if we were in the middle, it would be 1.42 million light years that way, another 1.42 million light years that way. And then these 2 points are now 93 billion light years apart, and I've chosen that because that's the observable universe now. What it really means is that the universe has expanded by a factor of 1,090 over those 13.8 billion years. So 2 points there over time have just been moving apart and are now 93 billion light years apart. Now what you probably can't really see even from this very clearly, it's very subtle, is the expansion slowing down for the first 7 or 8 billion years. So a very quick expansion rate at the start, slowing down, like throwing something up in the air. The gravity of the Earth would slow it down, so it would move up slower and slower. And then, weirdly, about the 7 or 8 billion year mark, the expansion of the universe started speeding up. This is when dark energy started to dominate the universe, so it became the dominant component of the universe. So it's a little bit hard to see, but if we just kind of squash up the units a bit there and then project out to 30 billion years after the Big Bang, you can see a bit more what's going to happen in the future. So that's continued acceleration of the expansion of the universe. If there was no dark energy and the universe was going to slow down in its expansion, this line would just continue and get slower and slower. But this is the result of dark energy as a cosmological constant. So, key points so far, the universe is made of 4 main components. Really, I suppose radiation is negligible at the moment, so the 3 big ones are dark energy, dark matter, and ordinary matter. There's a standard model of cosmology called lambda CDM, which is the mostly accepted model. We live in an expanding universe, and the expansion of the universe is now speeding up. So let's have a look now at ordinary matter and radiation. As I said here, these are the bits that we understand the best about the universe, so we'll just have a quick look at these 2 things. We'll start with the radiation, which is probably about 0.009%, so a very small amount of the energy of the universe. Might be a little bit more, a little bit less, but that's just kind of a rounded figure. So if we take the radiation and divide that up, we'll find that about 60% of this small amount is the cosmic microwave background, leftover radiation from the Big Bang. And what that means, if we were to go out into space and measure every cubic centimetre, if we could stop time, we'd probably count about 411 microwave photons per cubic centimetre throughout the whole universe. Now, you'd think that sounds like a lot if it fills the whole universe, but these are very low energy photons, these microwave photons. Hello.
I've just got a question. Why do you include neutrinos as radiation? Because they're really dark matter. They're a form of dark matter.
They are, but
Hot dark matter.
yeah. Now the reason I've put neutrinos here, this is the cosmic neutrino background. So that is what's left over from earlier in the Big Bang when protons, just after the Big Bang, when protons and neutrons were changing flavour from one to the other, releasing a lot of neutrinos. Now, it's true that actually what you say, at that time, the neutrinos would have been radiation at the very early time, going very fast, and have probably slowed down enough now that they are probably matter. So we can include that because it's such a small amount, only 0.004% of the universe. It doesn't affect the calculations now, but if we took it back in time to just after the 380,000 years, or even further back in the first 10,000 years or so of the universe, we'd find that they would be included as radiation. So yeah, it's a bit of a grey area, that one, really, because you can say it was radiation, it's slowed down, and now it's more particles. So it's a really good point there. Starlight makes up about 2% of the radiation, so that's the light from the stars, not the stars themselves, and that's the amount of starlight radiated over the history of the universe. And that's quite amazing to think that's such a small amount of the energy of the universe when we look out into the night sky and what we see is the stars. So we're just seeing a very small part when we look out at the stars at night. And if we move to the ordinary matter, the stuff we know best, which is mainly protons and neutrons and atomic nuclei, because the electrons of the atoms are only about 1/2000th of the mass of a proton. So we can pretty much say this is the neutrons and protons. Now, this is quite interesting, I think, the fact that ordinary matter makes only 5% of the universe, but of that, 93% is gas in the form of hydrogen and helium. A lot of it is intergalactic gas, so in between galaxies, in particular galaxy clusters, which you'll see when we look at the bullet cluster later on. A lot of gas in between, less gas in the galaxies themselves, but the stars and planets only make up about 7% of that 5%, which is a very small 0.35% roughly. So these figures, I say, are rounded, so I haven't bothered giving you a whole lot of decimal places, which would be kind of a little bit inaccurate since there's a lot of margins of errors, I guess, here as well. So if you think about the fact that stars are really the main mass of the solar system, the planets don't really count for too much when you think of it. This is mainly stars, which again are mainly hydrogen and helium as well. And so if you think of humans, we're just this tiny little negligible part, probably 0.00, lots of zeros, 1% of the energy of the universe, kind of bit of an afterthought there. So the ordinary matter, as I say, is the stuff we know best, and there's not really a lot of it that makes up the things we see. So let's move on now to dark matter. Dark matter, as I said, is probably these particles, cold dark matter, making up about 26% of the energy of the universe. This should really be probably called transparent or invisible matter because it's not dark in what we think of as dark, with, say, a black screen that absorbs light. It's most likely a particle or possibly a family of particles. There's no reason that it should be just a single type of particle when you think of, for example, atoms are made of up quarks and down quarks and electrons. So ordinary matter has a few families of particles, so dark matter may or may not, if it's a particle, if that is correct, may be a family of particles. And as I mentioned again, it's moving very slow, much slower than light, so we call it cold dark matter. Now it seems to be collisionless, which means that the particles of dark matter will just go straight through ordinary matter, so it's quite likely it's just flowing through this room as well. And dark matter particles themselves will probably just go through each other or very close to each other without interacting. I put a little star there because it's possible that in very high dense environments of dark matter that it may actually in fact collide with itself and maybe even annihilate. And if you have a look online, there's a video about the possibility that James Webb has seen hypothetical dark matter stars which are powered by dark matter collisions. So that's something to have a look at later on. And if that does turn out to be correct, that would be a good bit of evidence again for dark matter. I don't know if it'll be very easy for them to actually find out if it is dark matter causing these gigantic stars, but it would solve a few other problems in cosmology as well. The other thing about dark matter is that it interacts gravitationally, and that's how we have identified it. And it has the same effect as ordinary matter. So if you had a planet of a certain mass, we know that gravity is the curvature of space-time. If you had the same amount of dark matter and could squeeze it into the same volume and the same mass, it would just have the same gravitational effects as ordinary matter. So you'll sometimes find that matter in cosmology or on the larger picture of the universe is all just lumped into not 5 and 26, but sometimes just 31% of the universe is matter. When it comes to gravitational effects, that's often all that's needed for the expansion of the universe anyway. Now, why would anyone even think that dark matter exists? Well, in 1933, an astronomer called Fritz Zwicky was looking at this cluster of galaxies over here called the Coma cluster. And he found that the speeds of these galaxies rotating around each other seemed to be much faster than it should be. From the amount of mass that was in the cluster, just looking at the stars and the galaxies alone, these galaxies should have flown off into space. There seemed to be another 90% of mass of something that they couldn't see was required to hold these in place for the speeds they were moving. So he called this dark matter. You all know what he called it in German? Die Dunkelmatter. Matter. In 1939, another astronomer, Horace Babcock, was looking at the rotation of the Andromeda galaxy and found a similar problem in that the stars and some of the gas were moving too fast, rotating around too fast for what you'd expect from looking at the stars alone. That really, if the stars were the only mass in the galaxy, that the speed of these stars should rip the galaxy apart, they should just shoot out into space. And similar again in 1970, Vera Rubin and Kent Ford were looking at visible stars and the gas in Andromeda and other galaxies, and again found another similar scenario, that there seemed to be only about 10% of the required mass was in the stars. And you might remember from earlier that I said there's also a lot of gas that you can't see in the galaxies, but in a galaxy itself, the amount of stars much far outweighs the amount of gas. It's between the galaxies is a slightly different story. So it's interesting just to have a quick look at the physics of what this all means. So just a quick demonstration here. If we had this object A orbiting some mass, and the same object or similar object orbiting another bigger mass here, you can see that a greater speed's needed to move around this heavier mass. Otherwise, if it was moving this slow, it would just spiral in and crash. Or if this one was going any faster, it would just shoot off into space. So what that means is that the speed of an object orbiting something else depends on the mass inside, or is related to the mass inside the orbit. And that mass doesn't have to be a single object. It could be stars in a galaxy, for example, which is what we're looking at here. So if we look at the formula here, the answer to, or the mass inside the orbit can be calculated from the speed of the object and the radius of the orbit, so how far it is away from the centre. Just a bit of a simple formula there from Newton's formulas. But we can also calculate the mass of the stars inside the orbit from how bright they are. So if we calculate the mass of those stars inside the orbit, and that matches the mass that we've calculated from the speed of this object out here, then we know that the stars are all we need, that everything's accounted for. So here's that same thing again, everything's accounted for in this example. But over here, we've got the same number of stars that we can see, and we find this object moving a lot faster. So we know that the speed of that's much too fast for the visible objects. And that means there must be something else inside the orbit. So that's some sort of invisible matter, which we'll call dark matter. So that's kind of basically the idea, at least for the rotation curves in a galaxy, of why there must be some invisible matter keeping this object in orbit. And it'll be the same for all the individual stars inside. They'll all be orbiting the centre of mass as well. Now, to have a bit of a more realistic look, here's again a simulation. This is a simulation of a galaxy. It's by, who was it, Ingo Berg, I think. And I think it was Ethan Siegel, is another person who helped with it as well. But this simulation, which is quite a few similar things online that you can find, shows that if you look at a galaxy with no dark matter, and we look at the speed of the stars as we move out from the centre, we'll find that the speed of these stars is getting slower and slower as we move out from the centre. And that's called a rotation curve, and that's like a diminishing curve. Now, here's the same simulation, but in this simulation, dark matter has been added to the galaxy. And with the dark matter added, measuring the speed of these stars, we find that the speed stays about the same as we move out. And this is another rotation curve here. It gives a flat rotation curve. So you can see there's a difference here. It's due to the mass inside the orbits. So if we just have a look at a couple of other ones here, this varies by galaxy depending on the amount of dark matter, etc. in the galaxy. It might be a little bit of a higher rotation curve or slightly lower, but way above what we'd expect if there was no dark matter in these galaxies. And so that's what we tend to see, is something like this in galaxies in reality, except for one which we'll have a look at later on. This is the Triangulum galaxy M33. It's the third largest galaxy in our local group of galaxies after Andromeda and the Milky Way. Now, if we looked at just the stars and tried to work out what speed they should be moving at, it should be this line here, so that diminishing curve there, stars getting slower and slower, and out here the gas orbiting slower and slower with distance from the galaxy itself. But the actual observations show the speeds of these stars much higher than you'd expect from the stars alone, and even the gas out here is moving much faster. So you can see there's something, from what we saw before, there's something within their orbits of all this, even way out to here, so not just the stars, some sort of dark matter that would explain this situation quite well. This, again, is another simulation. This is with the Milky Way, and it shows just how spread out dark matter is from galaxies. So the blue is dark matter. The brighter the blue is the higher density dark matter. You can see there's a lot of these clumps or little high density areas of dark matter. Some of those will have dwarf galaxies in them, and some may actually just be empty and just have only dark matter. So one question is often, well, why is the galaxy in the middle, but all the dark matter out there, why doesn't it all just fall into the middle? Well, if you imagine before the stars and the galaxy were formed, if there was a lot of gas out here, the gas and the dark matter would all be drawn towards the middle, the higher density area. The gas would collide, the gas particles would collide, and due to friction you might find they'd move through, collide, go out a little bit further, but they'd lose a bit of energy, fall back in, slow down more, and eventually kind of fall to the middle. Dark matter, being collisionless, could do the same thing, fall through, but doesn't collide with anything, so just carries on right through and can just carry on with this big halo. So that's, in a nutshell, why ordinary matter tends to fall to the middle or be embedded in dark matter halos, whereas the dark matter can happily just sit out here. The particles are probably not moving super fast, but fast enough to just keep kind of orbiting around the system. So let's have a look now at another bit of evidence for dark matter. This is the bullet cluster. You've probably seen that picture online. And if I start first of all maybe with the amount of stuff in these galaxies and clusters, the stars make up about 1 to 2% of the mass of all this. The hot gas, about up to 15%, and the rest dark matter, maybe about 90% of the whole system. So I'll break this down now so we can see exactly what's happening. Get rid of all that artificial colouring, and this is what we see. We can't really tell what's happening just with our eyes, but it turns out there are 2 clusters of galaxies. This one here, which is officially the bullet cluster, even though the whole lot is often called the bullet cluster. This little one is called the bullet cluster, that's the main cluster. And what's happened is this bullet cluster has travelled through, or they both collided. This one's travelled all the way through to the other side of the main cluster. Galaxies generally are far enough apart that they're not going to collide, so happily just continue right through. And so that's what's happened there. But if we look at the hot gas using X-ray, this is coloured with the pink colour here, we can see that the gas has collided and slowed down, and so we kind of get the shockwave effect here. If I just go back, you can see the clusters are out here, but the gas has kind of collided and stayed in the middle. So that makes sense so far. We can see that that cluster has moved through. But if we use something called gravitational lensing and work out where most of the mass is for this couple of clusters, we find most of the mass is out with the galaxies. Now that would make sense if the galaxies were the most massive part, but we know that the gas between the galaxies and the cluster is much more than the mass of the stars and galaxies. So you expect if we use this gravitational lensing, what that actually means is if we get the light from distant galaxies, it gets bent by the gravitational field, just like a lens, and so it's called gravitational lensing. And so astronomers can work out where most of the mass is. And most of the mass is here and here. As we know, the galaxies and stars are the lowest part, so there seems to be something else out here. Now, if this is mainly collisionless dark matter, that would make a lot of sense. The dark matter, like the galaxies, would just continue through. The collisionless nature of dark matter means it should just follow with the galaxies to the other side. And putting them together, then we can get an inferred distribution of dark matter. The reason that's interesting is because proponents of modified gravity theories kind of need to find a way to explain why a modified gravity theory, if dark matter doesn't exist, if that's most of the mass, why isn't that where the lensing is occurring? So this is kind of in favour of dark matter as a particle. Unless something weird happens like space knows where that was going to be eventually and magically kind of works out and bends space there, which is kind of impossible. So I think that's one of the good reasons, or the best bits of evidence for dark matter. Now this is probably a good way to see it. It's just a little simulation by Dr. Andrew Robertson from Durham University, and it takes it's a simulation where, if I just stop it there for a minute, where the gas is coloured pink and they've put dark matter into the simulation, which is kind of shown up with this blue, and run the simulation, crash this smaller cluster, the bullet cluster, into the large cluster. You can see the shock wave there from the gas, so the gas is slowed down. But most of the mass is continuing out, which we know is not the galaxies, so it's something else continuing through. And that simulation, using dark matter as a collisionless particle, gives that same kind of effect there. So I think that's pretty good proof of dark matter, although I think there may be a few proponents of modified gravity who are saying that they can work out a reason for that, but I don't know if it's very really explains it that well. But there's more evidence of dark matter. That's not the only thing. Clusters of galaxies, where the amount of gravitational lensing seems to be due to a lot more than just the galaxies we can see. You may or may not know that the Milky Way's disk is slightly warped, and that can also be explained, again, in simulations. If we had some sort of tilted dark matter halo, that would give that same answer. The cosmic microwave background, these little dots, the redder dots are the warmer areas, the colder dots, the cooler areas, only by about 1 part in 100,000. But the physics of the cosmic microwave background is well known, and putting data into simulations again gives the same effect as what we see if we use collisionless dark matter to get to find out what this pattern should be. Without the collisionless dark matter in the simulations, we get a different answer. So again, this is another bit of evidence for dark matter. The large-scale structure of the universe, again, simulations. This is actual data, matching simulations. And this is, I think is quite interesting, just something fairly new from this year, Galaxy NGC 1277. Now the paper that this is in, this is a lenticular galaxy, which is kind of like a spiral galaxy, but a little bit older with lots of, well, not producing any new stars now, but we can also get that rotation curve of this as well. The rotation curve for this seems to be perfectly explained by the stars in this galaxy and doesn't need dark matter added to the calculations. So if dark matter didn't exist and we needed to modify our equations, the modified equations would fall apart with this. So at this stage, it's looking like dark matter as a particle seems to be the better hypothesis. It seems to require less tweaks and complicated additions to the science behind it. Doesn't mean that it is the right answer, it just seems that dark matter seems to have a lot more evidence. So dark matter, some bit of a summary of dark matter. An invisible matter which has been identified from its gravitational effects, makes up about 26% of the energy of the universe, and a good fit is some sort of particle or family of particles, and that it's a cold or a slow-moving particle. Let's grab a sip of water, and we'll get on to dark energy. So dark energy, lambda, a cosmological constant, makes up about 69% of the universe, and we'll have a look at why that's 69% in a moment. Now, it's fair to say we don't know what dark energy is. There's a high confidence that it does exist, and there are some interesting candidates. The best fit, as I've said a few times, seems to be something with a constant density throughout the universe with a smooth distribution. Something that doesn't dilute and grows with the universe, with the expansion of the universe. Now this stuff, whatever it is, affects the universe as a whole, so you kind of have to take the whole universe and look at the expansion through the equations of a large volume. And we know that there is something accelerating the expansion of the universe, and dark energy, I should say, is the thing that appears to be causing this. Well, it is what we say must be there to be causing the accelerated expansion. So how was it discovered? Well, in 1998, 2 teams of cosmologists set out to see what was happening with the deceleration of the universe. At that stage, there was no reason to think that there was an accelerated expansion. They thought it must be decelerating, so they wanted to see what was going to happen. So these teams were the Supernova Cosmology Project, which was led by scientist Saul Perlmutter, and the High-Z Supernova Search Team led by Australia's Brian Schmidt. What they wanted to do was see if the deceleration of the expansion of the universe, so it's expanding and slowing down, was going to stop and then collapse in with a big crunch, or if it was expanding fast enough that the deceleration was not going to be able to stop it, but it would just keep decelerating forever. So they had a look at distant supernova to work out the expansion rate of the universe over a good distance from where we are. and they found that it wasn't decelerating at all, but rather it was speeding up. Some of the distant supernova they saw were dimmer than they expected, and with a lot of calculations and work after thinking they'd made a terrible mistake and had to go and start again, realised that in fact it was caused by the expansion of the universe speeding up. So with that, we'll just go back a step and look at this flat universe thing that we talked about before. So this is the reason I brought this up earlier. If we remember our two-dimensional universe, and we looked at a two-dimensional flat universe with Euclidean geometry, then we have a look at our three-dimensional universe. The cosmic microwave background is the oldest light we can see. It's been travelling through space for 13.8 billion years, minus a little bit. And so that gives us theoretically a large distance to have a look at, to see what size these little spots appear on the sky. We know the physics, as I mentioned, very well, and we know the size that each of these dots should be when we look on the sky, the angular size. Now, if we know the size they should be, and we have a look and we see that they are the same size as what we see, we know, of course the answer's over here, we know that the universe must be flat because light is not being bent by the curvature of the universe. If the universe had positive curvature, we'd see that these spots look bigger than they actually were. If the universe had negative curvature, these spots would look smaller than they actually are. So we know that to a good approximation, well actually a very good approximation, that we live in a flat geometry universe, which is really good because you could have a lot of different amounts of positive curvature or a lot of different amounts of negative curvature, but only one flat kind of situation. So that makes things a lot easier, and it's kind of lucky for us that that is the case. So now that we've got those two things, we'll have a look at why this flat geometry can even help us from this point onwards. We want to know now how much energy there is in the universe, but we don't know how big the universe is, so you can't know how much energy there is in the universe. But we can work out the average energy per, say, cubic metre. So if we got all the energy in the universe and mixed it up so that it was nice and smooth, we could say, okay, in every cubic metre, how much energy do we have? This little symbol here, epsilon naught, the epsilon means the energy density, the amount of energy in a volume, and naught just means at this point in time. So we're trying to find out how much energy there is in a volume of space at this point in time in the universe. Now, here's a nice equation that you don't have to worry about too much until the quiz. What's that next? So this equation isn't actually as scary as it sounds. These are just numbers. The speed of light, that's the speed of light, that's 8, a number. That's pi, which we all know, and that's the gravitational constant. So that's just a simple number. This is the Hubble constant, the expansion of the universe, which is the thing we really need to know. And of course, I mentioned the Hubble tension, but we're using 67.7. This one over here, you don't even have to worry about. But it turns out that this thing kappa relates to the curvature of the universe. If the universe is flat, that's 0. If the universe is positively curved, that's +1, and this could be anything. If it's negatively curved, that's -1, and this could be anything. So as I mentioned, we have a flat universe, so we can get rid of that, simplify things down, and we find now that the amount of energy on average in the universe per cubic metre is simply just a number times the Hubble constant. This was derived from Einstein's equations by Alexander Friedmann, who has done all the hard work for us. So as I mentioned, that's just a number, 1.607, a whole lot more decimal places, times 10 to the 26. So 10 to the power of 26 is 1 followed by 26 zeros. Now, if we didn't change our units for the Hubble constant, of course, that would be 67 times that, which would be a huge number. But we have to use standard units, so metres, seconds, kilograms, and that comes out to a very small number. So we take these two numbers, multiply them together, and the answer is the average amount of energy in the universe per cubic metre is just less than a billionth of a joule of energy per cubic metre. So a very small amount of energy, which if you want to think about it in protons or hydrogen atoms, using E = mc² again, we can just take that, work out that that's the same as what about 5 protons would be. So we had a cubic metre and we had 5 protons sitting in it. That's the average density of our whole universe, energy throughout the whole universe. So that's good so far. We've got that. What does that mean? Well, we have this energy. We can measure ordinary matter, which we've already found is about 5%. Dark matter about 26, so that's the 5 and 26 that we saw before. Radiation now is negligible, so it adds up to 31%. So there's that 31% matter of the universe. So we're missing something here. We're missing 69%. If we have a flat universe, that's the answer. So the flat universe tells us that means, oh, it must be something else. It must be another 69% of something out there. We'll call that dark energy. Don't know what it is, but we'll call it dark energy. Okay, so that was the hard part. Now the simple stuff. We know there's something in addition to matter, dark matter, and radiation in the universe. We know 69% of the energy of the universe makes up this other stuff. We also know that we've found that the universe is accelerating in its expansion. So something is opposing gravity. Now, physics shows us that something with a constant density would cause this. What that would do is cause, I suppose you could think about it like a negative curvature, whereas mass gives a positive curvature, giving gravity. Something else that gives kind of a negative curvature. So something with a constant density would do that, and it's energy. So put that all together, we could say 69% of the universe is some sort of cosmological constant. So put it all together and we can find that that's how much dark energy we should have in the universe. Now again, that does depend on that Hubble constant. So we'll just go with this for now. Now, constant density, I suppose it's good just to have a quick look at what that means. And if we take our universe over here and just look at matter and dark matter, expand this universe, we can see that matter dilutes. So the density is getting smaller when it comes to matter. So that makes sense. But if we take this constant density stuff and expand our universe, we find that the more volume means the more of the stuff we must have if the density stays the same. So that's kind of the weird thing about this dark energy. It doesn't dilute like you'd expect with matter. So it's a weird kind of a stuff, this dark energy. So we have more space, more dark energy, and that does mean that there was less dark energy in the past and there'll be more dark energy in the future. Now, just a bit of a sidebar here. Quite often you hear, oh, dark energy is the force that does this, but it's not really a force, at least not as this lambda. And you can kind of understand that if you think about matter, maybe the Earth or a galaxy, we know the Earth's not a force, but it does have mass. Mass curves space-time, and the curvature of space-time is gravity. So matter has properties which curve space and end up giving us gravity, but matter's not a force. In the same way, dark energy is not a force, it's energy. It has properties which result in repulsive gravity, and so you maybe think about that as a negative curvature, might be one way of thinking about it. So it gives us the repulsive gravity. The properties are actually that it has something called negative pressure. And negative pressure is something it's a bit hard to kind of even get our minds around what a negative pressure would be. But this negative pressure doesn't actually move anything. It just has another effect of giving this kind of anti-curvature, giving us repulsive gravity. It's probably important to realise that dark energy has extremely weak effects. So what dark energy might do to us in this room here would be pretty much negligible. You'd have to look at it over huge regions of space of very low density. And so the universe as it is now, or as it's been even since about 6 or 7 billion years ago, the universe as a whole has become a lot more dilute, or the matter has in the universe. And so dark energy now has the ability to be the dominant component. So you look at it as a whole, not as just in little parts. And its only use really is to accelerate the expansion of the universe. If there is this energy everywhere in the universe, we're not going to be able to harness it for anything. So sadly, it's all there, but we can't use it. Okay, so what could it be? I mentioned it's probably a cosmological constant, something with a constant energy density. So a good candidate would be if space itself has energy. That would make a lot of sense. So if the universe expands, more space, more dark energy. So we think of a vacuum as being completely empty with no energy at all. So zero energy. That's the way we intuitively think of a vacuum or space. But quantum mechanics shows us that space actually has a non-zero energy for complicated reasons that we won't go into tonight. Something called the Heisenberg uncertainty principle means that there's an uncertainty between time and energy, just like you may have heard uncertainty between position of a quantum object and its speed. So you might know how fast it's moving, but you don't know its position, or the other way around. It's not that we don't know it, it's just that those quantities don't both exist at the same time. And it comes down to energy. So it means in the end, going straight to the answer, that space itself does have a non-zero energy, and this is an excellent candidate for dark energy. Vacuum energy, as I mentioned here, it's still ongoing subject of research. But just as a little aside there, there's something called the Casimir effect, which shows that there is something actually happening in the vacuum. And in this Casimir effect, take a vacuum, put two special conducting plates very close together, like nanometers apart, and you'll find that the vacuum energy gives rise to what they call virtual particles. And only certain wavelengths can appear between these plates if they're so close together, but more wavelengths can appear outside these plates. And it turns out this effect has been measured, and the vacuum energy will actually push these plates together. So we know there is a vacuum energy. There's been a few other examples as well. Something called the Lamb shift, which is the energy levels of electrons in a hydrogen atom, are slightly different to what you'd expect, but these virtual particles and this I think that's mainly in the electromagnetic field, cause a slight shift in the energies. So there is such a thing as this vacuum energy. Whether it's dark energy is still to be determined. There's other possibilities too, apart from Lamb. There's another thing called quintessence, which is a hypothetical quantum field, which is kind of a constant density, but not as constant as this lambda. It's possibly not the same value all through space, and it's possibly been changing through time. So if it turns out that this vacuum energy is not dark energy, this other thing called quintessence may be another candidate to be looked at. But all the observations from Planck satellite, etc., seem to point to this as being the answer for, well, I've got another talk on dark energy, but we won't get too much into that tonight. This is meant to be kind of introductory, so we've probably got a bit heavy already. So if we get now to the key points of dark energy, we know the effect of dark energy. It's causing the acceleration of the expansion of the universe. We don't know what it is. Observations suggest maybe vacuum energy, a form of constant density, and we know it's about 69% of the universe, meaning its density is about half to 0.6 of a nanojoule per cubic meter. So final thoughts, I mentioned we'd just look at the end at a couple of interesting ideas. These figures relate to the universe as it is now, 69% of the energy being dark energy, 26% dark matter, 5% ordinary matter. But if we go back in time, I mentioned also that dark energy must be less in the past, because if we go back in time where the universe was smaller, okay, that's another long story, but the universe was smaller. You could have an infinite universe which was smaller, but don't worry about that. So if we go back in time when the universe was smaller, dark energy must get less and less. The proportion of dark matter to ordinary matter is much the same, and is the same amount. Because the universe is smaller, then it will be starting to get more concentrated. So we keep going back and back until we get to that 7 to 8 billion years after the Big Bang, where I mentioned the expansion of the universe started accelerating. The reason for that is that the effects of dark energy on the accelerated expansion are twice the effects of the ordinary gravitation of matter. So when dark energy is a third of the energy of the universe and matter is 2/3, if that has twice the effect, then it's this point in time where it's going to become dominant. And that all fits too together with the various calculations. So we'll keep going back further in time when dark energy is getting less and less, and the matter of the universe, of course, was able to decelerate the expansion. Keep going right back, we're at 1.5 billion years, and now we're at 600 million. 200 million years after the Big Bang, dark energy is almost negligible, but we can see radiation is starting to have a bit of a more dominant effect. We'll keep going further and further, and then as we keep going further and further back, radiation makes sense after the Big Bang, a lot of radiation. So that is getting more and more dominant until we keep going further back. That's as far as my chart goes. But if you go back even further, it will become the dominant component of the universe. Now, to explain that, it's probably easiest to think of it going the other way. So if you think of all this radiation in the early universe, the universe expands. The radiation, of course, oops, go back there. The radiation will be, just like the matter, will be diluting. But it dilutes faster than matter because not only is it diluting, but the expansion of the universe is stretching the light waves, so they get a longer wavelength, which means a lower frequency and less energy. So that is losing energy with the expansion of the universe faster than the matter. And so that's why when we go backwards, we see radiation dominating. And the last point here is I mentioned that the Hubble constant is in a little dispute with this thing called the Hubble tension. So the cyan or blue coloured chart there is the one that we looked at earlier. If we change the equations around and put 73 kilometres per second per megaparsec, the upper kind of limit of this Hubble constant, it doesn't make a big difference really to the history of the universe. So it's not some major crisis which means the universe is completely different to what we thought. What it means is that maybe the universe might be a little bit younger than what we thought. It means that maybe there's a bit more dark energy and a little bit less matter, so the proportions are a little bit different. It's probably started accelerating somewhere between the 7 and 8 billion year mark as well. So a lot of research is pointing to this being kind of the closer value, so that's why I've kind of used that value. But that problem hasn't been resolved fully yet, so those are kind of the two extremes that we could probably look at. So that brings us pretty much to the end. So just a quick summary. We know that radiation is negligible in the universe now. Ordinary matter, 5%, is mostly gas. Dark matter seems to be a particle or a family of particles. We haven't detected it yet, so we can't be 100% sure, but it seems to fit very well as a cold, dark matter particle. It forms this cosmic web throughout the universe. And dark energy is the stuff that is now dominating, causing the universe's expansion to speed up, and it's quite likely a cosmological constant. And so that brings us to the end of tonight's talk. So, challenging questions, anyone? Yes. I knew.
One question and an observation.
Sure.
The question is, are there any projects underway to find an interaction between a galactic CDN halo and the globular cluster halo as a means of finding the metrics in terms of interactions? If there is one, that would be great. And then the observation is, if you want to see Casimir effect in real life, find a gecko.
Yes, I was going to say the gecko feed, that is one useful thing if you're a lizard. If you're a gecko, they stick to the walls using the Casimir effect, or anything, and ceilings. So the little tiny flaps of skin, I guess it is, on their feet, eh?
Yeah, it's basically little pads.
Yeah, little pads, yeah.
You actually manage to hit the Casimir distance. So like you see on the SCF scanning electron microscope.
Yeah.
Just the right size so the gecko is optimal.
So if you're a gecko, then vacuum energy or the Casimir effect is really useful. So,
I've got something just to mention. Brian Smith, who was mentioned here, the high-Z supernova team, he was actually a beverage speaker for us quite a few years ago now when he was quite a bit younger.
Yeah.
So I just thought I'd mention that.
Yeah. Good to get him back. It'd be really interesting to...
Yeah, we should do actually. I think he still lives in Australia.
Yeah, I think he does. Yeah.
Let's try. The other thing is there's another, as well as the Hubble tension, there's another issue that's come up from simulations that the universe is actually a lot less clumpy than it should be.
That's right, that's that S8, isn't it? They call it.
So there's something.
There's a few weird things happening, so which would be good because it would be really exciting if we could have some new science come along. So frustrating for some, I guess, if everything's kind of, well, not totally wrong, but frustrating for some, but also I think very exciting when this new science can come along. We learn a lot from it, don't we? So,
2025.
What's that?
2025. We're sending the Roman telescope out.
That's right.
Yeah. To pick up on dark energy and dark matter.
Yeah, and the
hopefully.
Yeah, that's right. And the Euclid telescope is up now, isn't it?
Yeah.
And they're trying to do the biggest 3D map of the universe, which will give us a lot of ideas on dark matter and dark energy by looking at what's happening with the structure and maybe able to put some of this together or pull it apart, maybe even. Yeah. And yes, talking about
survey for the halo. CDN versus the globular cluster halo.
Yeah.
Anything like that?
I'm not sure what's happening there. I know there is a few things going on trying to see if dark matter might be this particle called an axion and see if interaction with certain photons may produce another photon.
Like the findings in terms of the swap in polarity between the current dark matter with their best neutrinos, but they can switch, they can literally jump between being a muon versus electron neutrino on the fly.
Yes, yeah, that's
and
right.
That's able to find. There are thoughts that that's an interaction with the Planck space at 10 to the minus 43 on both space and time dimensions, but that's still in the state as far as I can remember.
Is that getting down to the quantum loop gravity kind of thing as well?
Not that, just that the Planck phone at 10 to the minus 43 seconds and 10 to the minus 43 meters is giving rise to a probability diffraction for a given neutrino. So it starts off life as a muon neutrino. This is back when I was in high school. It starts off life as from where it came from, but during flight, between emission and detection, then Heisenberg indeterminacy due to Planck space interaction will alter the probability of what the neutrino looks like when it gets there. So it's indeterminate even from emission point to detection point due to those low-level interactions. And there's been recent long-range work done from the far end of the visible to see that even that's occurred. That's also visible in the macroscope for measuring Planck space. That's all on YouTube.
Yeah, no, it's pretty fascinating. The quantum mechanics meets cosmology. It's kind of the smallest thing meets the biggest thing and kind of fit together. Not that I'm aware of, there may be, but I might not have kept up too well on that side of things. But there is thought though that neutrinos are what they call left-handed, so the way they spin and move, there's a possibility that they haven't seen yet is something called a right-handed neutrino. So it may be that a particle, we don't need to add anything else to the normal standard model of particle physics, that maybe neutrinos just under our nose somehow are.
They didn't found. But left and right hand literally are a uniparticle.
Could that be like quantum physics then? On like whether it's observed or not observed, which way it's doing?
That's exactly the thing. So it's the same as when you're dealing with a photon. The photon is its own antiparticle. In the case of the neutrinos, the handedness is equivalent. At least it appears to be on current experiments.
So let's hope that the Large Hadron Collider and other detectors and
they need a cameo Hyundai to pick up.
I was thinking more if they could maybe produce them at the Large Hadron Collider and maybe shoot them off down to the cameo Hyundai. No, that's right. Yeah, that'd be fun. Any other questions?
Yes, online.
Oh, yeah, sure.
Andy is asking, does dark energy support the multiverse theories? Yes.
I'm probably not up enough on the multiverse theories to be able to answer that too well, but if you go back to inflation at the start, the inferred inflation before the Big Bang, that seemed to be an accelerated expansion of the universe over a very short time, and that's maybe a kind of dark energy, and if that is turns out to be a real thing, which it seems to have a bit of evidence, then it may point to an inflaton field which may give rise to other Big Bangs and other universes. So in a way you could go back and if they can put the dark energy now and kind of match it up somehow with the inflaton field, then we may be able to look at that as an idea. And anyway, it's got some ideas about that.
Are we still headed for the big rip then?
Now the big rip would only happen if dark energy was something called phantom energy. And phantom energy would be something that is increasing in density. So vacuum energy nicely just sticks at one density, but if phantom energy existed, then we would end up with the big rip eventually. What we're going to get from this lambda is just a heat death, which is really dying of cold. They call it a heat death because it's kind of lack of heat. So that would be infinite future, just getting colder and colder. Yeah, there is a possibility of dark energy as that phantom energy, something called the equation of state, which kind of measures the pressure as a relation to the energy density. And this equation of state gives us a number called -1, which is lambda, but the values seem to be like -1.001 to -0.99 something. So there's a bit of leeway to go below the -1 and be the phantom energy, but on average it seems to be hovering about the -1, so I think we're pretty safe.
Any thought of it getting a name change from dark energy?
Yeah, I know, it would make a lot, yeah. Well, Sean Carroll, a famous cosmologist, said that he likes to call it smooth tension, which kind of makes sense, smooth tension throughout the universe, because tension is kind of like it's kind of what you maybe think of negative pressure as. And so he said if you called it smooth tension, it's something smooth throughout the universe.
Because you look at both of them together, you think they're
Dark matter, dark energy. Yeah, you do, and that's the thing. We need to call dark matter invisible matter and dark energy. Maybe we should start calling it lambda now and just hope for the best and get rid of the dark part.
I'm just going to say the history of lambda comes from Albert Einstein.
That's right, yeah.
Because he realised when he applied his equations to the universe that you couldn't have a stable universe. It was either expanding or contracting.
Yeah, that's right.
And but astronomers told him that the universe was stable.
That's right, yeah.
So he threw this lambda in to make everything work.
He didn't like wholeheartedly agree on it though, did he?
No, because he was a
He didn't
physicist.
like it,
He was a physicist, not an astronomer, so he had to rely on the astronomers to give him the data. So, of course, the astronomers thought, you couldn't see much else, that this is all there is. It's not collapsing or expanding. So you need to do something. And then he took it out, and then we find that it's probably right again. In maybe a slightly different way, but the idea of something cosmologically constant is kind of the general idea. So he was, yeah.
Any other questions for Jonathan? That's fascinating and very thought-provoking. Thank you, Jonathan.
Thank you.
Of course, without a dark matter particle, we wouldn't exist. We wouldn't have had enough clumping, gravitational
That's
clumping
right,
in the
yeah.
stars.
Yeah.
All these Mond people and stuff. Well, so how do you explain us? Yeah. So,
Fascinating fields.
That was very, very great, and we're grateful for you coming all the way up from Hamilton.
Thank you.
To
My pleasure.
chat on this. Thank you.
Enjoyed it.
Following on, so next month's talk is a PhD student from Auckland University talking about his research on black holes. So that'll be a very stimulating, fascinating talk as well. So it's great. So
Is he going to talk about the black holes as a dark matter possibility, dark energy possibility as well?
yes, he does. Yeah, the research that he's going to talk about. You probably saw a few months ago, early in the year, there was a question whether supermassive black holes could be responsible for the observations of dark energy. So he talks about that as well.
Yeah, I had something here, but I thought we've kind of gone through enough heavy stuff. I might have a quick picture. Oh, yes. So it was kind of, just quickly, I'll let you know. So the idea was that black holes, some of the black holes seem to be growing in mass proportionally to the expansion of the universe. So a couple of papers were kind of looking at this idea. which would make that a cosmological constant as well, because if they're growing in mass proportional to the expansion of the universe, then their mass divided by the size would be constant. And so the idea was that looking at old galaxies from 7 billion years ago, comparing to old galaxies now, the supermassive black holes in the middle seem to be 10 times the mass. 7 billion years ago, the volume of the universe was a tenth, so that seemed to match up together. So they're considering maybe we don't need dark energy as this thing I was talking about, but maybe black holes could be the answer. But it turns out that there's a lot of reasons to not think that's right, partly in the fact that if I just go through there, they're already accounted for in ordinary matter and maybe dark matter. And a paper also by Auckland University, Sohan Godler, Sohan's the one who's going to be talking next. So he's going to be talking next, and J.J. Eldridge put together a paper, that said that, well, black hole merger rates and masses don't seem to fit that idea of black holes being dark energy. Rotation rates in certain galaxies don't seem to match it, and Hawking radiation would kind of go out the window if they don't, if they're growing that fast. So it's a neat idea, and there may be some other science that comes out of it, but it seems to be one that's kind of falling apart now. So, but anyway, come along next month and
the author who's actually doing the talk.
So that'll be really interesting, I think, to hear what he has to say about things. Fits in quite nicely.
Yeah, very good. Thank you, John. Everyone drive home safely.